Hello, ladies, gentlemen, and in between, and welcome back to another episode of Maths with Hamblin with your beautiful host, Hamblin. And today, my boys, we're going to be taking a look at and deriving the equation of our first curve in 2D space in the xy plane, a straight line. It's going to be fun. Let's go. Okay, so the first case we're going to consider is a straight line that cuts right through the origin, and it passes through the point 0, 0, where x equals 0 and y equals 0. And to find the equation of this line, we're going to have to find an equation involving x and y, which on every single point of the line, for every single x and y value on the line, that equation is satisfied. I mean, that sounds like a really difficult thing to do, but if you're clever, here's something interesting you might notice. Consider a general point on the line. Doesn't matter where it is, as long as it's on the line. And let's say that point has coordinates x, y. Let's draw out the y-coordinate as this little height here. You can see that is the y-coordinate, and same with the x-coordinate here. Okay, cool. Let's do it again. Let's do it for another point, say way up here. Y-coordinate, oh, cutting through my own drawing, and then all the way back down here. Now, what's so interesting about this? I'm going to give you 5 seconds to see if you can notice it. Here it is. These two triangles are similar, which is very important. If you remember what similar triangles are, they're triangles that are just scaled up versions of each other. Imagine if you were in Word and you expanded the image like that, which means their sides are all just a scalar multiple of each other. Now, if you want me to prove it, here you go. This big triangle's little angle here is obviously the same as this one here. They both share a right angle here, and this little triangle's angle is the same as this big triangle's angle. So, by this angle relation, these triangles must be similar. And what that means is that if you take this side and divide it by this side, it should be the same as this side divided by this side, because they're both in the same ratio, they've both got the same dimensions. So what that means is that for any single point on this line, its y-coordinate divided by its x-coordinate equals a constant. It's always the same number, which I'll call m, and which has a special name, the gradient. And now, if we rearrange this, we get y equals m times x. The famous equation you guys all know and love, with this coefficient here, m being the gradient. Now, you might say, but Jake, this, you've only proved it for this positive quadrant here, where x and y are positive. Surely things would break in the negative bits. Negatives always screw up everything. No, my friend, no. Let's take a look. Let's take another random point here, boom, with a negative x-coordinate and a negative x-coordinate and a negative y-coordinate. Now, notice that these triangles are just 180-degree rotations of each other. I know they're not the same size, but that doesn't really matter here. They're 180-degree rotations of each other, which means that their sides will still have the same proportion. But what about the negatives? Well, if you take negative y and divide it by negative x, you're just still going to get a positive number. So in fact, this gradient is the same for everything on the line. So there we go. We've shown that an equation which is satisfied for all x and y coordinates on the line is y equals some constant times x. Bada boom, bada bing. On to the next case. Okay, this will be a quick one. I just want to take a look at a line that has a negative gradient, because last time we looked at a line with a positive value for the gradient, which in that case is any line that goes like this, like that. As long as it crosses through this quadrant here, it will have a positive gradient. I'm sure you can see why. You're very clever. Now, why did this line have a negative gradient? We'll take a look at this. If we again take any general point on the line, label its x and y coordinates, you'll notice it's got one positive coordinate but one negative coordinate. So when you divide the two coordinates to get your gradient, it becomes a negative number. So in this case, it will be, the equation of this line will be y equals a negative constant times x. And that's brilliant. And the second thing I wanted to show you with this little side note is, because of the last thing I showed you, where you can just draw similar triangles and it's okay, you can calculate the gradient in pretty much any way you like. As long as you draw a triangle like this and like that so that it touches the curve, you can just move it back down here and you can see that it's still a valid way to calculate the gradient. So if you're ever looking at a line and you need to calculate its gradient, which you will need to do, then you can just draw any triangle like this and then you can calculate the gradient with a known y-coordinate and a known x-coordinate, which is just fantastic. Okay, so we've fully covered the case of a straight line that goes through the origin, and it has equation y equals some constant times x. Now let's look at the slightly harder case. Okay, so now we're going to consider a line in its full generality, a line that can be any orientation, any height above the x-axis, anywhere at once, and we're going to find the equation of that line. So, first of all, let's take a second to consider what we've got here. Okay, well, we've got some random line and it's some height above the x-axis, but this is a bit of a problem, right? Because we only know how to calculate the equation of a line as long as it passes through the origin. Well, that's not no problem. We can just move this line down, calculate its equation according to there, and then we'll use a function transformation, and I'll show you what I mean. So, let's move this line down so that it crosses the origin. Boom, now it crosses the origin, that's brilliant. And we've got to make sure here that it still has the same gradient because, well, we've only moved it down, so it's going to have the same gradient. And from here, this is amazing. We can just calculate its equation as y equals mx. But, ooh, sorry, dropped my pen. But this line is not, this line is not this line, it doesn't have the equation y equals mx. So how can we get from this line to the line we want to find the equation of, any general line? Well, if you remember from my function transformations video, all that's happened is that this line has been shifted up some amount of units up the y-axis. To be specific, if we look at where the origin's gone, the origin got shifted up to here. And we're going to call that point the y-intercept point. And it only has a y-coordinate, no x-coordinate, and let's call that y-coordinate c. So this is just the equation, this line anywhere is just the equation of a line that passes through the origin, y equals mx, then shifted up c units. And if you remember from my function transformations video, we can easily write this as, sorry for the messiness, y equals mx. So that's the equation of this first line before we shift it up with some random gradient. The same gradient as this line, if you recall, but then shifted up some plus c. And if you don't know why that works, just watch one of my function transformations videos and you'll see why. So, bada bing, bada boom, we've got our general equation of any line, because by shifting the value of m, we can change the steepness of the line to anything we want. And by shifting the value of c, we can move it up and down any which way we want. So, I mean, that's amazing, right? To get the equation of any line, you just need to draw any triangle on the line. You can do y over x and get your gradient value. And then you just need to look at where it crosses the y-axis, and then you've got your y-intercept, and you've found your equation of your line, and it's all perfect. We've only got one more thing to discuss, and let's discuss it quickly, and that'll be it for this video. Let's go. Okay, this last thing I wanted to discuss is just a little bit of a side note, because you're probably used to seeing this equation. You were taught it in GCSE or whatever education you got. The equation of any general line is y equals mx plus c. But in A-level, they like to shake things up a bit and give you different forms of this equation. Still the same equation, just in a different form. And I'll quickly show you how to get to that form and what it means. So, we've got an equation here involving y and x, and we can just shift these around, and it's still the same relation, right? It will still generate the same line, because there's still the same x and y values will still satisfy it. Okay? So we can just, for example, shift this over, get y minus mx equals c. Okay, that's kind of interesting. Y minus a constant times x is the same number each time, all across the line. That's kind of interesting. But also, we can also just multiply the equation by a number. That's also okay. For example, let that number be a, and then we've got what ay minus amx equals a times c. And now, because these are random constants, it really doesn't matter what we call them. I'm gonna keep this one as a. I'll rename this to b, so plus bx, and rename this to c. So boom, there we go. This is what I wanted to show you, the other general equation of a line. This is the form you'll most commonly having it given to you. And in order for you to find your important values, your gradient and your y-intercept, you're going to have to rearrange it so you've just got y equals blah, blah, blah. Because if you remember from the derivation, the gradient and the y-intercept were only valid as they are if you've got y equals something or other. But yeah, that is the general equation of a line. It looks very beautiful if you ask me, and don't get tripped up. This c I've written here isn't the y-intercept. It's not the y-intercept at all. Remember, I did all this nasty stuff and rearranged the constants. But yeah, other than that, that's all for this video. You now know more detail than you ever need to know about the equation of a line. I hope that's been satisfactory for you, or you learned something, or hey, maybe you're just watching these for fun, in which case, love goes out to you. Anyway, my name's Hamblin. I'll see you next time. Goodbye.